Okay, hello, good afternoon, everyone. Welcome to the fourth event of the Energy, Sustainability and Circularity Seminar Series, organized by the Department of Chemical Engineering, University of Liège. My name is Motiar Rahman. I'm an assistant professor at the Department of Chemical Engineering and the coordinator of this seminar series. The main goal of organizing this seminar series is to listen to the expert to a range of topics related to energy and sustainability. Let me take the opportunity to introduce today's speaker, Dr. Philippe Ajais. Dr. Ajais is a research director at the French Alternative Energies and Atomic Energy Commission, CEA. He carried out research on carbon-based supercapacitors as part of his PhD thesis at CNRS, then BATSCAP, between 2006 and 2011. He joined the CEA in 2011 as coordinator of a research and development program dedicated to new generations of lithium-ion batteries. Between 2016 and 2020, he led several academic and industrial projects at the CEA, and in late 2020, he joined the CEA's Energy Programs Directorate. Since 2022, he has been the director of the Priority Research and Equipment Program, and in early 2024, he joined the Program Agency for Decarbonized Energy, which was established in December 2023 by President Macron. Without further delay, I would now like to invite Dr. Ajais to take the stage. Philippe, please.
Okay, thank you, Motia, and thank you very much for this invitation. Also to Nathalie. I will try to summarize the situation regarding the energy systems. It will be a quite brief introduction regarding the systems because I could speak hours like this. Feel free to ask me questions after the presentation. Of course, it's an open discussion regarding this energy systems introduction. A few words just as an introduction of this. Just remember that uses and needs define the solutions, not the other way around, because it's very important to identify the solutions after identifying the needs and the uses. It's due to the fact that it has limits, the physics and the humans. There's two things that depend the solution. I will skip this, but it's very important to identify that it's very important to defossilize our energy systems all around the world. But we have to take into account many things as impact, for example, the climate change, the availability of resources, impact on biodiversity, and that's the fact that it's very important for our survival itself, and not only for our humanity, but also all the other things around. And a few words regarding the energy systems. Go to basics. Energy system, what is it? First, you have to identify what is an energy vector production, what is a conversion, what is storage. In between, you have transport here, as you can see, between these energy vectors and these converters and these storage systems. And all these kind of things has to be managed and controlled, whatever the situation. And it answers to uses, and the energy system is this. All these things all together, not only energy vector production, not only the conversion or the storage. It answers to uses, and you have to keep in mind that when we speak about the energy system, it includes two things: the energy chains, that most of the people consider as to be the physical aspect, and the other things that we consider as to human, social activities and organizational systems and associated mechanisms, such as, for example, the sociological, political, legal, etc. And you have to take into account all these two things, these two pillars, to identify energy systems. And most of the time we also make some confusion between the energy itself and the energy vectors. And there's some confusion to the fact that sometimes the people consider the energy as to be the energy vectors. We only see the consequence of the energy as to be a movement or electromagnetic radiation, for example, wave, can be, or also can be a heat. This is only the consequence that we can see. That not confused with the energy vectors, which is only a way to transport energy from one place to another one. It is, for example, the case for electricity, heat, gas. You can transport these things from one side to the other one. And finally, if we make a short little exercise in our mind, you know that for a long time that energy is the power by the time, and you can't destroy energy. It's very important to keep in mind. You only transform the things and transmit and transport. Some order we take the legs, for example, we can the leg power and energy, and we assume that we are human. And what we could provide with this? The power of the legs is roughly 100 watts, arms is time less, and the energy obtained that you obtain if you pedal for 7 hours is roughly 700 watt hours. So that's 7 hours multiplied by 100 watt. Based on this energy that we consider that you can store, for example, if you use a generator and then you store under a battery, for example, with an ideal energy convention, then you can, how much time you can consider to use, for example, a vacuum cleaner power with more than 2,000 per watt, correspond to roughly only 20 minutes that you can use this vacuum cleaner. And if you consider a car, an electric car, an EV, for example, and a conventional car, not a huge one, not a Tesla Model S, but just a conventional one, you only spend 3 minutes to discharge all this energy stored, only to go 1.5 kilometers. So the question of efficiency is one first thing that you've considered. And the second one is the use. What is the efficiency of the use of this electricity or this energy? And what is important too is not only to conclude based on the average values, but you have also to identify what will be the exertion, the range of this energy consumption and the power associated to this, to avoid all the erroneous conclusions. Because our needs fluctuate. Of course, you sleep. Sometimes you sleep, sometimes you move, and that's the reason why our needs fluctuate all around the day. For example, electricity use is not the same during the night and during the day. So you have also to look at different time scale, very tiny scale, but also for large scale, because you can also some order of magnitudes in mind. And there's nothing completely that I will show you today. Few technological reminders, just to clearly see the things after. You know the power. The power is this. So some figures for this. You already know this kind of magnitude of the magnitude. Power is not. It can be very huge, but you have also to consider also the time if you want to consider the energy. And energy is not the same. For example, when we think about an explosion or 1 kilo of TNT, you would say, okay, it's huge energy. No, it's not the case. It's roughly half of the daily intake for an adult today. Only the power is huge here because the time is short, and their daily intake is not taken in one quarter a second. Some example of energy. And two values that you can store in your head. 1 liter of petroleum is roughly 10,000 watt hour, and 1 liter of lithium-ion module is roughly a 20th of this value. So that means that you replace 1 liter of petrol, which is a primary energy, to a secondary system, such as the lithium-ion batteries. Of course, you can't replace this at once. You have to consider other things. You know that there are 7 types of energy, and most of people generally make some confusion of this. Energies, not energy vectors. Energy means that we have gravitational potential energy, what we say mechanical energy, only linked to the mass and the weight. An hydroelectric dam is only a converter, it's not an energy. It's just a mean to convert some energy to another one. For example, a windmill that uses the kinetic energy is not an energy, it's a converter. The third one is the caloric energy, the heat. The fourth one is the radiative energy. For example, PV panels is not an energy; it need a converter. When we speak about the renewable energies, for example, is not focused on the PV or the windmills, but it's only focused on the wind and the light. The fifth one is the chemical energy. This is the huge one that most of people use. Fuel cell, thermopower station, lithium accumulators are only converters, it's not energy. Again, nuclear energy, nuclear power plant is not an energy, it's only a converter. So the nuclear energy is linked to the mass. And the seventh is the electrical energy, but it's only linked to the people and the electricity, mainly, most of the time, is on
I think we have lost the connection. Philippe, hello?
Can you hear me again?
Yes, we can hear you, but
okay.
Yeah, it's fine. Yeah.
Just shut down at once. So I don't... okay.
Yeah.
I was there. It was okay. See? Can you see my screen or not?
Not
yet.
See
my screen? Not yet.
Not
okay.
yet.
Again. Okay. Share.
Yeah, it's coming.
It's okay?
Yeah.
Does it work? Okay, I was there. Yeah?
No, not
okay. No.
We don't see the slide. We just see again the participant list. We can't see your
slide. The slide?
No, not yet. We can see the list of participants.
Wait. Yeah.
Now, yes, it is coming. Just a second.
Does it work?
Yeah. Yes. Perfect. Yeah.
Okay, I will move this. Okay, I was there. You heard me?
Yes.
There?
Yes, please continue.
Okay. Regarding the energy vectors, the electricity is a way to transport some electricity from one side to one. So the network, the electricity network, the grid, the power grid. When we focus on the energy itself, it's only capacitor that we consider as to be a way to store some electricity, pure electricity, without any transformation. Electricity is an energy vector. Heat is an energy vector. You can transport some heat using heat networks, distributed heat networks. There's other way to transport energy. For example, transportable fossil fuels. For example, it's a way to transport some energy. So it's an energy vector in this case. Electromagnetic waves, for example, when you use an optical fiber or a magnetron in a microwave, for example, it is an energy vector. And the mechanical movement can be also a transport using some springs or using some closed circuit using mineral oil, for example. This is energy vectors that we have not to confuse with the energy itself. Let's pose the problem. Why we are so much interested in the energy system? First, because you use all the time some energy, but you don't know most of the time how you use energy and what are the transformation between this the primary energy that the nature provided us and this final energy corresponding to your bill. So it's a way to supply these energy vectors to you, and finally your comfort that correspond to the usable energy or correspond to your choices. And from this primary energy to this usable energy, finally, you have many, many losses due to the fact that you transport the energy, due to the fact that you transform the energy. And of course, there are some losses, and you have to make some choice to have impact on the primary energy and final energy consumption. Another very important things that you have to know is the load factor, because most of people make some confusion between the installed capacity and the real usable energy that you have and the real power that you can access. And we use this load factor to correspond to the energy that you produce by a mean during 1 year, a reality, and the energy that could produce this mean if it worked all the year round at the maximum power. And it's important to not confuse with the installed power. Most of the time, people that want to push as much as possible some specific system will consider sometimes the load factor and sometimes the installed power or installed capacity. Take into account, for example, the French case. The installed capacity in French, when you sum the capacity, the renewable capacities, for example, windmills, and, solar power plants, and hydroelectric, these things are correspond to more installed capacity than nuclear power plants. But unfortunately, the load factor of these windmills and photovoltaic park is pretty low. So that's the reason why we need a huge amount of installed capacity to provide some energy. And energy corresponds only in few percent for the case of solar power plants in France, and 15% of the energy that we consume in France is provided by the windmills. So most of the energy today is provided by the nuclear power plants in France, electricity, not the energy, due to the fact that the load factor of nuclear power plants are huge, is very high comparison to the other things. So the load factor varies very little with the technical improvement. So if you multiply by 15, I would say 15 or 20% this load factor of photovoltaic in one park, that means that you will have larger access to the light. Is not the case. We will not change the situation of France where we are. So that means that it depends on climatic conditions and the consumption needs, not on the technologies. Just to better understand the situation. If you consider the load factor for, I would say, a system that we can manage properly, which was the case for the gas turbines or for the nuclear power plants, you can access to this very high load factor. But regarding the windmill and the photovoltaics, of course, the load factor is you have to take into account where you produce and when you produce. So it is the case of average values for all the year, but of course, during the night we'll have no electricity from photovoltaics, and sometime in the winter we'll have in summer you will have no access to electricity produced by wind powers. So that for electricity production means linked to the meteorological and climatic parameters, the load factor is very dependent on the geographical location. And finally, that's the reason why each country has to make its strategy, and because the final cost cannot therefore be the same everywhere. For example, in the south of Spain, or considered in Scotland, of course, the load factor will not be the same for photovoltaic, and then you will have a strong impact on the investment and depreciation. And you have not to confuse this load factor with the efficiency of a converter. For example, for the PV panel, the conventional PV panel is between 25%. Some other magnitude of over fossil fuel to electricity systems. I will not detail all these things, but you have to keep in mind that you have to consider that to be very different from the load factor itself. Another thing that you have to consider when you speak about the energy systems is to identify what will be the footprint itself of the system. If we compare in power density or in energy density, of course, the values are not the same. whatever the system, of course, you have a footprint. That means that you have also a footprint on the resources. So you have to extract the resources from the earth to transfer these resources and to build the systems itself, which we say is the gray energy. And this gray energy has also an impact on the availability of the system itself. And when we size the system, we must take into account not only the energy or the power itself, but to meet the usage, but we have to take into account the more restrictive of the two systems, the energy or power, because it defines the sizing itself. So why we are so interested by this? Just come back in the past, long past, just after the Second World War. Here are the CO2 emission, equivalent CO2 emission in the world, and what we can see is finally, if we were in the trajectory of between the 19th century and 20th century, we would say, okay, there's no dramatic impact of the humanity on the carbon emission. But finally, since the Second World War, we have accelerated by a huge factor this trajectory. And that's the reason why we have so much impact today on the CO2 emissions all around the world. And at the log scale, as you can see, we have a huge, strong impact of this CO2 emission that we have to consider that, of course, it can have an impact itself on our Earth. And of course, there's an impact on the CO2 emission and the concentration in the atmosphere. As the thing that you can see, there's an alteration between winter, spring, and summer. You have this alteration, but the biomass cannot extract the CO2 from humanity itself, and then there's a huge impact of the CO2 emission, that the acceleration of this CO2 emission in the atmosphere. And there's an impact, of course, on the temperature, and now we are sure that there's a huge impact from the humanity on this CO2 emission, and then the latest impact is the heat. So we have a climate change now all around the world with different impact where you are, depending on where you live. In the South or Europe or America or in Japan or in China, you will not have exactly the same impact itself. Unfortunately, we have a global energy consumption that is increasing year after year. And when we plot this CO2 emissions and this global primary energy consumption by resources, what we see, there's a huge amount of fossil fuels consumption in the world during the two latest centuries. And we can plot also the CO2 emissions. As you can see, there's, I think, I would say, a strong correlation between the CO2 emissions and the use of fossil fuels. Some people would say, okay, it's due to the fact that we have increased strongly the demography in the world, but finally is not so much impact. During the three latest quarter of century, we had an impact of, we multiplied the demography, the population by 6.4, and the CO2 emission was multiplied by 6.4, but in the same time, the population was multiplied only by 3.2. So that means that we accelerate the CO2 emission strongly with the development. This is the thing that we can conclude today, is not only due to the fact that we have a demography that is increasing faster, but also due to the fact that we have also a huge need due to the fact that we increase the development of the countries. Here are some examples of this increasing of CO2 emissions. And what we can see is if you take order of magnitude of India, for example, between India and France, today you have a factor 2, and between France and China, you also made factor 2. And between China and United States, you have also a factor 2. So what will be the responsibility of each country is the question today. Because when we emit some CO2, you do not emit in close to our frontier. It's all around the world. So you have to focus on the responsibility of each country. Of course, you can have some acceleration, for example, in China. And now that try to slow down this CO2 emissions. This is the case, for example, since 2024 in China, they slightly slow down the CO2 emissions. And of course, this CO2 emissions correspond to our needs. And of course, we need more and more materials. The more you increase the development of the country, then the more you increase the energy needs, and then the more you need to extract the materials itself. And basically, we could say that the richer you are, the more CO2 you emit. It's roughly the trend that you observe here on the graph. And while we are focusing on the energy, first, due to the fact that when we consider energy here, it corresponds to these CO2 emissions that we have all around the world. And of course, energy is just the elephant in the middle of the living room. And these CO2 emissions are not only due to the fact that we have some transport, because if you average the world scale, the electricity and the heat correspond only to a third of the overall CO2 emissions. Transport is only 15%. But depending on the country where you are, for example, in France, it's 32%. It's twice this value that we observe at the average of the world. Constructions and, of course, industries and deforestation, there's also impacts. Agriculture, there's also impact. So we have to consider all the sectors, and to decarbonize all these sectors, we have to focus on how to defossilize as maximum this part of coal, gas, oil, and of course the use of biomass. You have to rationalize as much as possible the biomass, because it's the only way to extract the CO2 for the Australian field. And if we try to identify, okay, what are our use and what are the sectors where we emit, which kind of use we have, here you have the sectors, here you have the use, and here you get the type of gases, because CO2 is the major part of the CO2 equivalent emission, but you have also other gases that you have to consider, methane, and you have also nitrogen peroxide, and also F gases, fluorinated gases. And here are the sectors, here are the uses, and here are the gases. And of course, you have some cross between these sectors, the gases, and the uses. And each sectors, we identify, whatever the country, what are the most emitter, what are the main part of the emissions, and which kind of solution we could provide for these sectors. Of course, we cannot for all the world, for this, okay, for example, in Belgium or in France, we have to consider our scale, what we can do at our level. Finally, when we focus on France, what in France are complex energy systems, so we produce roughly the same ratio of CO2, methane, fluorinated gases, and nitrogen dioxide gases. But France is only a tiny part. It's roughly 1% of the CO2, then less than 1% of the CO2 emission around the world. Europe is only a tiny part too, but we need also to import most of our needs from all around the world to Europe to support our development. And in France, the transport is the main part. Agriculture, forestry is also a large part. And due to the fact that we desindustrialize more and more the manufacturing industry and the construction in France, then of course we have observed a decrease of CO2 emissions because we have less and less constructions. The primary energy, for all the countries, we can do the same. So the primary energy, the summary, and also to identify what would be the final consumption, energy consumption at the country level. In France, the question is not to decarbonize electricity because it's already the case due to the case that we have hugely developed the nuclear power plants. It's one solution, but of course it has some impacts too, how to store our nuclear residues. And it's also the case for all the countries, but it is not developed at the same when you consider all the countries, the European countries. For example, here in Belgium, we have roughly reached 160 something gram of CO2 per kilowatt hour of electricity. Electricity is only one part of the problem. And when we focus on this Belgian electricity mix, what we can see, of course, we slightly decreased the CO2 emission per kilowatt hour. You slightly increase the renewables, but still have a huge part of fossil fuel use to produce electricity. You still have some nuclear power plants, and finally you come back to the nuclear power plants to try to decrease more and more this CO2 emission for electricity. But the electricity is only one part, as I told you. In Belgium, it's only this part, but you have to decarbonize the industry, the transports, the residential, so all the things, all this part has to be decarbonized as much as possible. It's also the case in France. In France, it's only a quarter of the overall energy need that we have already electrified. So that means that we have to decarbonize this part in gray as much as possible. And this electrification and decarbonized heat are going too slowly to have a strong impact on the CO2 emission at the national level. And the final energy consumption is falling very slowly and largely linked to the fossil fuels, unfortunately. It's just another way that we have also some dependencies. The net imports is huge. We can consider also the aspect on the financial aspect, the economical aspects. These net imports are huge. And then we have also an impact on the final energy consumption. We have some losses, essentially due to the fact that we can't use the heat from nuclear power plants to be valorized as a heat that can be used in other systems. And what we could do, just to summarize the situation, is this. So we have claimed that we would like to electrify as much as possible our use. Okay, great. But when we see the growth of this electrification, finally, we have connected all the nuclear power plants during this 25 years. And since this time, we have slightly increased the electrification of uses, and the target is there at this national level, just to reach 55% of the electricity used in our final use. This is a huge target, and I think year after year, we have to consider that maybe we will not reach this target. And of course, all these uses have some carbon footprint. And not only the transport, some impact, also the food, how to house, how to administrate the state, how to equip, what we import, as you can see. The imports has a strong impact on the carbon footprint of the state. And when we try to summarize the situation today, of course, we have to consider not only the national at the national level, but we also to consider the imports and the impact of these imports. Everything is an impact, just to summarize the situation. And who can say, okay, I'm neutral today regarding the carbon emission? I think nobody can do that today. The second part that we have to consider is the heat, because when we consider the heat in France, it's also the case in Belgium. It's a significant part to be defossilized. It's roughly 45% of the CO2 emission that we have to consider today at the national level is only the heat production and essentially at the low temperature is the case. I will detail this just after. And so what we can do today, we'd like to decrease as much as possible the CO2 emission and the greenhouse gases emissions. So what we can do, we have three parts to consider. The first one is to shift from our fossilized electricity to decarbonized or defossilized electricity and decarbonized heat. The second part is to decrease also the consumption, so to consider also the sufficiency. Sufficiency is a huge impact because you have to consider there is some societal appropriation. And sometimes the people say, okay, we will increase also, if we increase strongly the price, that was the case during the beginning of the Ukrainian-Russian war. As soon as you increase slightly the prices of heat or electricity, then the people try to slightly decrease the consumption. In France, that was 7% on impact. And the third thing is the efficiency, how to increase the efficiency of the whole system. Of course, it has some technical improvement, and also to change from one vector to one with more efficient conversion, when we can consider that to decrease also the consumption and to decrease the greenhouse gases emission. But of course, when we consider all those things, we have to consider not only at once what there's impacts, but for a long time impacts at what is a geographical aspect, and also for duration, with the time we will have some impacts. What impacts on what scale? And you will decrease the price of the system if you can duplicate the solution for many, many other countries. Then the question is how to anticipate, how to change the system itself by modeling and to confirm the things by experience. When we consider the Kaya relationship, which is written by Kaya in 1993, this CO2 emission corresponds finally to the population. This we have no level, finally, quite no level. At a term, we should reach 10 billion of humans, I would say. The second one is to consider the GPB per population. That means that to decrease slightly the consumption and to change the use. The third one is to consider the energy by GPB and correspond to the energy efficiency. And the fourth one is to use the decarbonization, so to electrify as much as possible and to use as much as possible the low carbon heat. Finally, this first parameter, we will have no consideration on it because we'll slightly increase year after year. The second one is to consider the sufficiency, and the third and fourth one correspond to the technologies. And when we consider more technology or more efficiency, I would say both. We have to consider both things because without any sufficiency or without any technologies improvement, finally we can reach the target to decarbonize as much as possible the world. And today there are the two pillars, the sufficiency and technologies. Okay, what we can do based on it. So we have many solutions, existing solutions. We have the energies at once, we have energy converters here, and we have the energy vectors here. You provide some electricity, some heat, some gases, and based on these energy vectors, you can also perform some transformation, some conversion. And for example, at home, you can have some refrigeration unit, you can have some radiators, and you can also transform these energy vectors to other one using some machines in between. Let's summarize the situation. Okay, we must decarbonize all the systems that are not already decarbonized, but we have huge things to do. Whatever the scale, taking account the special and temporal situation, and we have to consider that all systems are often interdependent. So you will not produce only heat. Generally, you need to produce heat using some other vectors. To reach the target, we have to consider that it must be reliable, because we will invest for a long time, because when we change the system, we invest for decades, not for 1 year or for months. And we have to consider also that it has to be some customer or to be acceptable by the citizen. It must be at an acceptable cost and to be secure in data, in materials. So if we have no access to strategic materials to build the systems, then it's not so safe to do that. And to decarbonize, we just tackle the energy system, the storage system, the means of conversion, the means of production, and the means of management and piloting. We have to consider all these four things, not only the production or the conversion. And of course, we have to consider not only the energy efficiency, but also the green energy, the impact of resources, and also to take into account the recycling at the national level or the European level, to be sure that the things that we have extracted can be reused in some other field, and to be valorized, not to be scrapped like this and that's it, because there's no second Earth. So when we can imagine, for example, just to try, okay, today most of people try to push as much as possible renewables. Okay, but to decide, can we completely replace the controllable means by intermittent means? Let's try. We take the example of France. That was only the case of France. We can apply these things over countries. We have one PhD working on it today, and we have the consumption for 4 years. This is the real situation. As you can see, there's some variation year after year. And this is the average value that we have in France in black line here. So of course, our consumption is not phased with the production. So we have to adaptate the production and the consumption and to be at roughly the same level between the consumption and the production. Let's consider an intermittent things. That was the production scaled with the fictitious mix with 100% of wind power. Of course, there are some negative values because sometimes there's some consumption, but there's no production. That's the reason why we are below zero. And if you consider the PV, of course, we have this situation. We have sometimes that we have no production due to the fact that there are intermittent things. So to equilibrate the system, that means that we have to consider the storage, not only the production. So we have a direct impact on the storage to have the same services as we have with the controllable system. What corresponds to the store, the quantity of energy that we have to store, if we would like to replace and to have the same use of electricity in France, by other means. And that means that we have to compensate this electricity that is not be produced during the winter and sometimes summer for the wind or for the PV. Then in this case, we have to compensate by 70 hours a week. So it means a huge amount of storage. Again, in the PV, we have to adjust for 20 hours in a day. It's a huge quantity of electricity, but we have to also consider the seasonal change during the year. That means that we have also an impact in 1,000 hours in the year, but 2,040 hours, 400 hours in a year. So that means that we can't replace itself in France. Maybe some case in other countries, but in France not possible, and in most of the European countries not the case. We have to consider the mix between some piloting mix and some intermittent means. Fortunately, we have chosen, and this was the case in Belgium, that was also the case in Germany. We use diverse mixes. That's the reason why we have developed not a single solution, but various systems. The second thing is to consider that intermittent megawatt hour, so energy, has not the same usage value than one controllable megawatt hour of that you can produce when you want. So please do not compare costs and impacts on the existing of the power plants. It's no sense. You have to consider the additional cost for storage, for networks, for piloting, for management, and also the costs are directly linked to returns. Regarding the heat, if we consider the global level, roughly 50% of the final energy consumption is just required to produce some heat. So that means that it accounts for roughly 40% of greenhouse gases. In France, is 45%, so roughly the same order of magnitude. So when we consider, we say, okay, we have to focus on the transports and we have to focus on, okay, first you have to focus on the heat. So the heat is this. So we have a huge amount of greenhouse gases emission, whatever the sector where we are. And when we say, okay, we produce some heat, it's generally for industry or for buildings. This I will skip. And if we summarize the situation today, 45% of the global of the CO2 emission There's more vulnerable things, and solutions exist today. So for 75% of the problem that we have today to decarbonize the heat, we have already some solutions, existing solution that works. The question is not a problem of solution, it's mainly a problem of cost. Access to this low carbonized heat with an acceptable price. Due to the fact that fossil fuels are pretty low price. This I will skip. And there's some solutions. For example, in the case so one thing that we can do to store some heat water during the summer and to use this stored water during the winter is the case. It exists, for example, in Denmark, where the thermal heat storage exists for large systems, for example, in Vojens. We can see that we can access to a pretty low price of heat for large systems and only using some heat. It's not PV panels here, it's only thermal panels where we heat only water. And due to the fact that we use only low temperature of water, then we can store for long term with a low price. It's also the case with the gases. Belgium is, for example, made the focus on the gas uses, but the gas is a CO2 emitter. It's roughly 40 grams of CO2 per kilowatt hour equivalent electricity, and it's roughly 220 grams of CO2. Is huge emitter. So we have not to consider CO2. The gas has to be a way to decarbonize the system. It's not a way to decarbonize itself, the system. You can store the gas, but the problem is you have some, most of the time the people use this gas only to heat at low temperature. To heat a building at low temperature using some combustion has no sense, because you heat usually the temperature tend to degrade the quality of energy, what we say exergy quality. And of course, we store is the thing that we can store quite easily in France, also in Belgium. But the question is which kind of impact has this gases emission? This I will skip. Just to summarize the situation, we know that we want globally to decrease as much as possible the CO2 emission. Most of people try to work on the heat or work on the electricity. Imagine that you have 1 kilowatt hour of electricity. What I can do with this? I can do that. So I can perform some electrolysis based on water. Then I will obtain some hydrogen. And this hydrogen can be stored and used in a fuel cell or a motor using a fuel cell, or to directly be used in one internal combustion engine. And you can see that the efficiency is pretty low due to the fact that the efficiency of reaction is pretty low. You can also perform some Fischer-Tropsch, and you will be able to produce some methane, some e-fuels with a pretty low yield of reaction. And then if you use an internal combustion engine, we will use only for 1 kilometer for 1 kilowatt hour of electricity. But this hydrogen is required for some of chemistry use. That's the reason why more and more people focus not only on the use of hydrogen for mobility, more and more on the chemistry use. Due to the fact that we will need this hydrogen to replace some carbonized hydrogen, we say. Carbonized hydrogen is some gray hydrogen or black hydrogen from fossil fuels to be replaced by electrolysis, or we never know, white hydrogen. The second thing that we can do is to say, okay, I will use this electricity to store some electricity using electrochemical reactions in sodium-ion or lithium-ion batteries, and then the efficiency is quite high. You can reach between 6 and 8 kilometers for passenger car, or you can choose to produce some heat using a heat pump. Then 1 kilowatt hour of electricity will produce roughly 3 kilowatt hour of heat at 80 degrees. And then you can store this heat at low temperature during some months, or to recover this heat for your uses at home. For example, for some days, this is the case for domestic heat water. So finally, what we say, that for this system, the efficiency is very high, but will not answer with these things to this chemistry uses. So finally, we use all these things to answer to our decarbonization of the systems. And when we consider the storage system, we have to consider many parameters. The first one is the performance, of course, the energy density, the power density, the energy efficiency, etc. The durability, because number of cycles that we'll access, of course, has an impact on the revenues and the chemical question. And the operation conditions, for example, temperature. So you have to define the use to identify what will be the solutions. Coming back to the first slide that I shown to you. Of course, the cost and externalities, because you have to secure the things and to finance the things. And so you have to consider the environmental aspects, because we try to decarbonize. But if you replace one mean by another one, but we will emit or ever have other impacts that will be higher, there's no sense. Generally, we have many data for this aspect here and less data for this. And less people try to share, of course, these things, because business is there and physics is there. Let's consider a storage life of 20 years with maximum 7,000 cycles. So charge, discharge of the system. What we can consider. That means that if we want to reach 50 euro per megawatt hour of cycle, so roughly the cost that we have today for the production means at the European level, that means that for one cycle per day, that means considering the number of cycles and the number of years, that means that we can invest roughly 350 euro per kilowatt hour. If we have less cycles during only one cycle per week, that means that we'll divide it by 7. That means that we have only 50 euro per kilowatt hour for the investment. And if we have one cycle per month, it's only 12 euro. And if we consider only one cycle per year, that means only 20 cycles, you have to consider only 1 euro per kilowatt hour. So the longer you want to restore, the more cheap storage you need. It's very important, because sometimes people consider that hydrogen will be the solution for other things, but finally it's not the case, especially for the interseasonal system. To store hydrogen in large sites is a huge impact on the environmental aspect and a huge impact on cost. And finally, you will never reach 1 euro per kilowatt hour at this level. Just to summarize the situation, so reminder, energy resources means source of carbon emissions. And we can consider 3 kinds of things. The first thing is the stock of energy. So in this case, we have large densities. Historically, we have access to these fuels. So that means we have access to fossil fuels, to nuclear and energy decarbonized system. We have also the renewable to human energy. It's considered that a large density energy, but we have low projected resources. So the aspect is we have no large access. So everybody wants this, but finally we have a pretty low access, and the cost, of course, will increase year after year. It corresponds to biofuels. The fourth one is the flow energy. It corresponds to weak energy density and intermittent availability. So we consider renewable and recovery energies that are decarbonized. You can consider the sun, the wind, the hydro. Sometimes hydro has to be considered as a stock energy. Geothermal can be also considered to be a stock energy. And of course, you have some geological impacts. So whatever the situation, we have seen that today we can have strong aspects, some impacts, and some link that we couldn't anticipate for a long time, that we have identified that we have dependencies between countries. What we try to avoid is the fossil fuels. This one will be more and more rare, and this one is dispersed and fluctuating in energy, but finally perennial. So that means that if it is dispersed, we have to modify the infrastructure to produce, to collect, to store, to transport, to distribute. The second one, the second aspect, fluctuating, that means that we have also to identify what will be the environmental aspect, the social cost, and what will be the impact on the extracted materials. So we have to delete this one to prioritize this energy here and to massively integrate, but taking account many aspects, the losses, the load factors, and to prioritize as much as possible regarding the uses that we have. So the use must guide the choice of the energy system again. And we know that we have already some uses that will be difficult to project in the future uses, and there's some impacts. Some people in France has tried to do that and to not confuse the decarbonization of the energy and decarbonization of electricity. The use of the decarbonize is a priority, so we have to decarbonize transport, we have to decarbonize the residential, so home, the tertiary sectors, because in our developed countries, such as Belgium or France, we have huge impact also in the tertiary sectors, the industry and agriculture. If we take just focus on the heat and the CO2 emissions regarding the largest emitting industrial site in France, we have mapped the things, and what we can see is we have, of course, we got large sites that can emit strongly, and we have focused a plan today to decarbonize these 50 largest sites in France. But you can see also that there's a huge impact from agriculture that represent roughly the same ratio as these 50 largest emitting sites. But unfortunately, to decarbonize these 50 sites has an impact. Some people will leave using their industrial site to other countries where they accept to emit. Or, so if you constrain strongly the agriculture to be decarbonized, it corresponds to roughly 140 farms, 1,000 farms. But of course, the diffusion, the emissions will not be the same, and the cost that the people can pay for this is pretty low. And this I will skip. So we can do two approaches to decarbonize the system. What we say a bottom-up approach. So we start with the bricks, we have large panels, we assemble the things, and finally we identify where we could have an impact. The second one is to have a top-down approach. So we identify the constraints of the system level, then break down the constraints on the bricks itself and the interface, because between the bricks we have interfaces to identify the location, what will be the mass, the volume, the quantity of materials, etc. And we identify areas for improvement, and today the strategic plan is based on this approach, to create and to build new systems to be more efficient than before. And more people try to develop this system approach and not this brick approach. And few words regarding the modeling, it's close to be finished. There's two ways, finally, just to try the things or to model the things. But to model the things, sometimes you need some other additional things, and to perform only experimental works. Sometimes you can't anticipate and you can't accelerate on decarbonization because each use will have different impacts. So this is why it's very important to focus on not only experimental works, but also on modeling, and to be able to speak it together, to collect the data from the past data, and also to be able to plan for the future uses. And due to the fact that you will invest strongly on the system, because it's CapEx intensive, hugely CapEx intensive, to transform the system at the national level, then you will have to make some good choice, appropriate choice that be supported by experimental works and also by modeling. And the prerequisites of this to carry out some modeling is to have some modeling tools, of course, to collect some data for a long time, not only the technical sheets, it makes no sense, because you have to be able to identify what would be the dynamics, the transitories on the other systems, to also to be able to describe properly each component and what will be the emphasis between each means. It's very important to be able to build the things properly and to challenge each bricks and to challenge all the systems to adjust at the maximum of the system. Generally, we work on the multi-level a multi-vector system. So from the component to the national level, and also from the national level to the territories, networks, and the components. And generally we take into account two main vectors: heat and electricity, and generally gases. When we consider renewable gases, for example, hydrogen, or for example, biofuels, for example, generally it corresponds to a dependency to heat and electricity. That's the reason why we consider, for example, hydrogen to be a second vector, not a primary vector. And more people try to develop this kind of model to accelerate the transformation of our system, but we have to take into account also not only the technical aspects, but also the environmental aspects, the economical aspects, societal aspects, because more and more people try to push for small systems, but there's some constraint from social aspects. When we want to implement a new system, most of the people will say, okay, I don't want this system. We would say a certain NIMBY, not in my backyard. I don't want to have these kind of things. Of course, I would like to develop as much as possible renewables, but finally, I don't want to have windmills. I don't want to have photovoltaics, etc. That's the reason why we have to consider the social aspect. And of course, it's a multi-scale and multi-approach, multi-vector approach, from the, would say, vehicles to the buildings, to the industrial sites, to the city, and finally to the national level. And we have this now to this bottom approach, so the top-down approach. We have to consider that what will be the impact considering all the interfaces. And generally, it's the most difficult things to do, to manage interfaces between the systems. And if we consider also what would be the logical way to consider the systems, most of people, since for a long time, consider the things as to be the most profitable things, and we have to consider another way to think the things, just to have a logic of systemic risk management. So, how much will it cost later not to do it now? So we have to develop a more resilient system, not to consider only we have to install these things now and not to consider a long-time approach. And the thing that the people has done, that I will skip, but we have more and more things like this developed at the international agency, the multi-criteria analysis, to consider not only the CO2 emissions, but also to consider the CO2 absorption, what will be the relevance of the compatibility with the public policy's objectives, and also to consider the cost, the benefits, the risk, and to consider what would be the imbalanced things. This I will skip because it's too long things. And if we summarize what we have to do, we identify that we must to electrify as much as possible and to identify some priorities. Consider that we will push as much as possible electrification of the use in France. Here you have the efficiency, so of 1 megaton of CO2 avoided per terawatt hour of electricity. And here is the electricity consumption. So that means that if you replace 1 million by another one, and then of course you will avoid strongly the CO2 emission, then it will be high here, and here correspond to the actual usage and the impact of the deployment of this. If you prioritize the things, it's like this. First, you have to, as much as possible, to consider the road transportation electrification, direct electrification. That means that you use as much as possible batteries, because it's the most efficient way. The second one is to replace the space heating, low temperature space heating, also the hot water heated by fossil fuels, by heat pumps, because it's very efficient at all and correspond to roughly, to replace all the road transports and the heat, the space heating, correspond to 250 terawatt hour of electricity. If we consider other uses, for example, to replace to decarbonize as much as possible the steelworks, or also the existing H2 uses, it corresponds only to these two parts that we have to do again, but it corresponds to a tiny part of electricity consumption, but with a lower impact. And finally, if we want to replace the aviation and maritime uses that we have today in France. We could apply exactly the same things in Belgium. You will use huge amount of electricity, but to the fact that the efficiency of transformation, of conversion of this electricity in some generation of fuels, then the efficiency is pretty low, roughly 13%, then you consume a huge part of electricity just only to move the people using by aviation and maritimes. That means that the first thing that we have to focus on is the electrification of road transports and the low temperature heat. So some conclusions, and we'll finish with this. First, we have to consider the sufficiency aspect, not only the technological aspects, because we are in a closed system, the world, and we have to achieve the decarbonization. We have to also to consider our uses, how to use electricity, how to use heat, how to use gases, and how to transfer between energy vector. The transfer between energy vector is a solution, but it must be model, not only to test and again to test and again to test to identify what would be the overall impacts, not only the technological impact, but also the grey energy impact. You have to keep in mind that there are already many solutions that are available. The question is, okay, what we have to manage is the first thing that we have to consider, and it must be as much as possible inexpensive to have an impact, and we have to consider also the lifespan of the system. Not at the installation, but the overall lifespan of the system. And the fourth things that people forget most of the time is to perform some socio-technical researches, because if you want to push as much as possible the defossilization of the system, you have to have the population on the energy system, also to support these choices, and to be sure that we will not change the territories without any human involvement. And I think that's it. Thank you.
Thank you very much, Philip, for this insightful, excellent lecture. Yeah, the presentation was really nice, and I hope our audience really got some good overview on energy system as well as the pathways to decarbonize our society. I think now the floor is open for questions. You can either ask the question directly to the speaker, or you can write down the question. I can read it for the recording. Okay, so I think we have got the first question. I will read it for you, Philip. Why are biofuel and biogas considered as parts of the solution, whereas burning them releases as much carbon dioxide as burning their fossil equivalents?
Okay, maybe I get some slides for this, just to better understand what would be the impacts. Wait. Maybe I got this. Wait. Because it would be easier to show you what would be the impacts to replace one by one. Yes. Otherwise, I can do that by hands. Yes. Okay. If we consider the situation, for example, in France. In France today, we need, just for France, only considering the gases. Today the gases consumption is 450 terawatt-hour per year. And if we summarize only the situation for the existing uses of gases, of course, you could not replace by using biomass, because we have estimated in France, we have performed huge work on it, that we could replace only between 75 and 140 terawatt-hour per year, using all the biomass, the available biomass for this. So that means that it's only maximum a fourth of the required gases that we use. And if we focus only for the transportation, it corresponds to only the logistics for the transport, for the road transport. So that means that you have to avoid all the heating, all the industrial uses, all the high temperature uses. So of course, everybody wants this, and then you will have a rising of the price of this biogas because everybody wants this, and there's not over availability of biomass because the biomass is the only way to capture CO2 efficiently.
Great. Next question, please. Okay, we have another one. Earlier in the slides, you mentioned that electricity generation and transportation are only a small part of the carbon dioxide emissions. However, combined, it was about half. Isn't this a significant part of the problem? Also, do you know what part of road transport is for potential use compared to shipping? For example, trucks.
Yeah. If you consider all the transportation, is roughly the same situation in Belgium or in France. Transportation is roughly a third of the CO2 emissions that we have globally at the national level. And if we want to electrify these systems, it's more efficient than to use the primary energy because the primary energy that we use is fossil fuel. And when you use an internal combustion engine, the average efficiency of this kind of engine is a fourth, so 25%. And that means to use electricity is more efficient. That's the reason why when I plot the things, that's the reason why we have not 700 something terawatt hour per year dedicated to transport, but only a third of this value, because to charge and discharge using a battery, you reach roughly 75, 80% of efficiency. So that's the reason why it's more efficient to use electricity to recover some energy, to recover some electricity in the battery, and then to store this electricity in the battery, and then to use this electricity that you have stored using a e-motor. And of course, it's limited. And when we consider the transportation, the logistics, the road transportation and the passenger car, roughly you have roughly the half. So half dedicated to the transportation for logistic, and considering the trucks, the buses, coach, etc., is roughly a half. And taking into account also the light commercial vehicles. And the other one is passenger car, and it's half. So you can decarbonize already all the passenger car, all the light commercial vehicles, more and more trucks and buses are electrified. It's the case already in China, and they are pushing more and more these solutions. And there are, of course, various solutions to answer this, but most of people push on the battery system, not, for example, the hydrogen system, due to the fact that we have huge efficiency using these systems. And you have lower impact on the primary consumption of energy.
Okay, so I think we have another question from Mark. Thank you for your answer to my earlier question, which explained why biofuel and biogas will never be enough to replace fossil fuel and gas. But my question was, in what are biofuel and biogas more valuable than fossil sources since burning them release as much carbon dioxide?
It's another question. Yeah. When we consider biomass, of course, it's not zero impact. When we consider, for example, to produce heat using biomass, only without any transformation, for example, today we consider that the CO2 emission per kilowatt hour of electricity using biomass is roughly 70 grams of CO2 emissions per kilowatt hour electricity. So it's not zero, because you have some transport of the biomass to transform this biomass. You have some residues. You have to collect and recycle the things. And when we don't consider a life cycle assessment of the whole system, is not zero. Only on the CO2, you can capture some CO2 using the biomass, and you consider short cycle. But when we consider all the overall impacts and the transformation and the grey energy that we need to perform this, the use of the biomass, then we will have some impact. And burning, of course, the biomass has an impact. And we consider that we have a cycle. So you emit some CO2, then you will capture the CO2 using some biomass, and then you can recycle. This is what we say, the cycle of carbon, the carbon cycle. And the carbon cycle life can be short. For example, if you consider some grass or some cereals, some things like this, of course, can be a yearly cycle. But if you consider, for example, in the forestry, then the cycle will be larger, a very long cycle. For example, for oak forestry, the cycle is between 30 and 50 years. So you can say, okay, I cut the grass, I recycle, okay. But if I cut a forestry, then you have to consider a long cycle, and then you can't recover the CO2 at once. And then you have CO2 emission at once. And the question is, what will be the CO2 emission that we'll have, and what will be the CO2 molecule impact for a long time? And unfortunately, as soon as you emit some CO2, not only 1 year after, you will have the loss of CO2 at once. The duration is roughly 1,000 years in the atmosphere. So you have a long time of this CO2 emission impact in the atmosphere, in the oceans. Acidification of the ocean, for example, comes from the CO2 emission for a long time. And before transforming this CO2 in geological capture, for example, in carbonate, it takes long time. And there's a reason why we take into account the long cycle life and the CO2 emission cycle, considering not only at once we have replaced one grass by another one, but also how to recapture the CO2 in the long life cycle life. I hope it answered to you, Mark.
Okay. We have our next question. Technical solutions exist, but the difficulty seems to combine them properly. This is also a question of policies. Any examples of bad policies applied in Europe that leads to counterproductive effects?
Yeah. Yes, that was, for example, the case for the gas. For example, if you replace, just one example, very simple example. I want not to push on the fingers on German people, but because there are some friends in Germany, but the choice was sometimes to push from the coal power plant to gas power plant. But if you take in account the fugitive gases emission, finally it's roughly the same, because at once you have 3% of fugitive emissions using the gases, you have roughly the same life cycle assessment as coal. So finally, to replace some coal system by a gas system has no sense finally. And huge amount of money was dedicated to this replacement of coal to gases. But we know that we have implemented new systems without any effects, which is the case today. There's no effect, real effects when we take the overall assessment. And unfortunately, as soon as you have invest on new means, you will use this means for almost 20 years. So that means you have kept the system for almost 20 years because we not replace before 20 years. This means because the investments were huge and the storage of gases has a certain impact, has to be provided and amortized as much as possible, and the financial aspects. So you have to consider all the things, not only the replacement of the means, but the overall chain, and finally, what will be the impact of dependencies between your country and other countries. And that was the case of the dramatic way of choice for Germany. For example, they have decided to work for a long time with, for example, with Russia, to have this Nord Stream 1, Nord Stream 2, to have this gas supply. But unfortunately, they've developed their dependencies to Russia. And it's very difficult now to come back on it due to the fact that they didn't consider the overall system.
Excellent. Any further questions? Okay, I have one very general, maybe your suggestion or overview on the following comments. Like we're talking now about decarbonizing our society, which is the most important thing, just to get rid of this fossil fuel use and just emitting too much of carbon dioxide in the atmosphere. So what, in your opinion, would be the should be the first step? Like if we start dealing with or trying to if we try to solve this issue from the immediate basis, what would be the very first step we should take? Between these two, maybe, or you may add it afterward, but from my viewpoint, should we bring batteries to the transport and use batteries more and more, or we should use e-fuels for the circular economy? So
I would
what
say,
should be the
I would say that the first thing that you have to do, because it's more efficient at all, is to have some sufficiency approach on the things. For example, the road transportation can be easily decarbonized, but I think we try to replace one car by one. There's no sense. The first things to do is just to admit that we can maybe think differently using our transports, maybe to replace one car by other way, for example, to use one car and less car in cities, less car and transport. For long distance, for example, we could imagine not to use the car, which is more efficient at all. And I think the first thing is to do that, to focus on the road transports, because it's a huge impact. The second one is, of course, to focus on the decarbonization of the heat, because most of people forget it, and it's very efficient to and very easy to decarbonize today. And we can see it's the case in France, it's also the case in Belgium, when we replace some gases by electricity and using a heat pump. Whatever the electricity that we have in Europe, it has a benefit impact to use this electricity. Also in Poland, where the electricity is highly carbonized based on the coal fire plant, due to the fact that the coefficient of performance is very high with the heat pump, and then we can develop and have less dependencies on fossil fuels that we mainly import in Europe. The second thing is, of course, we have to consider the e-fuels, but e-fuels will be limited by the access to electricity. And when we go back 10 years before, most of people said, okay, we have huge amount of electricity, we will have renewables everywhere, we will have a huge way to store. Finally, when you consider the whole system, when you have to consider renewables plus infrastructure reinforcement plus conversion means plus storage, then the overall cost finally is higher than to use directly the electricity itself to produce something that will use that directly. Because storage, the best storage is the storage that will never develop. And of course, e-fuels can be used only for very dedicated application where you can't use batteries, where you can't use hydrogen, only if you have identified one very specific field, sectors where you say, okay, in this field, I can't replace the things, but also take into account sufficiency. If it is to supply some e-fuels only for planes, it has no sense, especially if we consider that more than 50% of the use of flight is dedicated to go to Canaries, to go to Antigua, no sense. It's only for leisure, not for very efficient things.
Excellent. Okay, so if there is no further questions, let's give a big round of applause to our speaker.
Thank you very much.
Okay,
I will send the slide. Welcome. I will send you the slides.
Excellent. I have some end remarks as well. Before I close today's event, please allow me to have a few closing remarks. Big thanks, Philippe, again, for accepting our invitation. and for delivering this excellent, very nice talk. And of course, many thanks to all of you for joining us today and making this event a success. We will be announcing the next event of our seminar series in August, as the next event will take place after the summer break, most probably in September. The advertisement will appear on our departmental website and our LinkedIn page. Thank you very much. Have a nice afternoon and excellent week ahead. Thank you. Bye-bye.
Thank you, Mota. Thank you, everybody.
Merci.
Thank you,
Bye-bye.
Nathalie. Bye-bye.
Bye.